Thank you for watching. I'm Brad Murray from Duke University, and on behalf of the team of the project evaluating the effects of adaptation strategies on Ocracoke Island, I'm going to present a brief overview of coastal processes that form the backdrop for the project. And we'll start by talking about the natural processes on barriers and how those natural processes interact with the human management actions that people take in response to natural processes, and talk about how we can use computer models to try to understand how the interactions between the natural and human actions lead to different landscape configurations under different management strategies. To start with, long-term chronic shoreline erosion is clearly an important part of this picture. And this graph is showing the rate of shoreline change along the length of Ocracoke from the west to the east, and it's showing it for different time periods represented by the different colors. So we can see over toward the east, this is the erosion hotspot that's been consistently eroding over all these time periods, and farther west, some time periods have been eroding and some accreting. To understand what causes this long-term shoreline change, we can draw an imaginary arbitrary box along some section of the coastline and ask, what is the balance of sand coming into the box versus sand going out of the box? And if over the time scale of years, there's more sand coming into a box than going out, then the beach is going to be gaining sand and the shoreline will move seaward. The shoreline will be accreting. On the other hand, if there's more sand leaving over the scale of years than coming in, then the shoreline will be moving landward or eroding. The balance includes both sediment that's moving in the alongshore direction and sediment that's moving in the cross-shore direction. We'll talk about them in turn, starting with the alongshore sediment transport. Now, this just arises because breaking waves stir up sediment, they stir up sand, and they also generate a subtle current that then carries that sand along shore. And if you go to any particular place on the shoreline and measure how much sand is going by each day and add it up, you'll find that there's some net transport over, let's say, a year, and that net transport tends to be different from one part of the shoreline to another. So if there's, in this case, less sand coming in one side of the box in the alongshore direction than is leaving from the other side, losing sand, shoreline is eroding, and vice versa. Green arrows showing gain of sand that corresponds to shoreline accretion. At other times, that part of the shoreline has had a negative balance and shoreline erosion as well. Now, this alongshore transport is always occurring and it just accumulates over time. On the other hand, in contrast, the cross-shore transport is very episodic and it's related to storms. And one of the most important aspects of storms is how high the water level gets. This is the water level that includes both the storm surge and the extra elevation that waves tend to produce when they break. And if this total water level is lower than the height of the dunes, then a lot of sand tends to get moved offshore, and that causes a bunch of shoreline erosion. However, during the fair weather times after the storm, that sand moves back on shore and the shoreline comes back to the same position it was in before. So in the long term, this kind of cross-shore transport related to storms does not contribute to the long-term chronic shoreline erosion. On the other hand, during storms where the total water level is higher than the dunes or higher than the sandbags in this picture, then the waves are going to carry sand landward and deposit it on the top of the barrier and the interior part of the barrier. This is sand that comes from the beach and near shore seabed, and so it's going to tend to make the shoreline move landward, makes the shoreline tend to erode, and this is not temporary because that sand that gets deposited on the barrier doesn't come back to the shoreline. So while this contributes to chronic shoreline erosion, these overwash processes, when waves go over the tops of dunes or erode through dunes and deposit sand on the barrier interior, this every time this happens, it increases the elevation of the barrier a little bit. This is why barriers occur in the first place. And this is why barriers persist, even though sea level's been rising for many thousands of years. This tends to increase the height of the island in the long term at the same rate that sea level is rising. So from the perspective of creating and maintaining the landform, overwash seems like a positive thing, but clearly storm waves and sediment coming onto an island are hazards for humans. The waves and sand damage infrastructure and structures, and it's very understandably a set of processes that humans will want to try to prevent or mitigate. And when overwash does occur, we need to bulldoze the paved surfaces and tend to put the sand back to rebuild the dune line to try to minimize or prevent the next big storm overwash event. And as much sense as that makes in the short term, in the long term, the more successful we are at preventing overwash, the faster the landform tends to disappear because it's not gaining the elevation and maintaining the width of the island the way it does when overwash occurs intermittently. Now, to use computer models to investigate this very coupled set of dynamics between the human processes and the natural processes, the main idea is to start by representing some section of the landscape with a model domain represented by the elevation in each of a lot of model cells. So elevation here is shown relative to sea level. So blues are below sea level and browns show the dune line. And an important point here is that with this kind of a model framework where elevations are represented relative to sea level, representing sea level rise means that all the elevations tend to decrease over time, just decreasing relative to sea level. Okay. Before we look at the animation on the right, I want to walk you through how one model that represents barrier evolution under natural processes works. And this barrier 3D model, each model year starts with a year's worth of sea level rise and adds a year's worth of dune growth, and then represents all the sediment transport that happens during the storms during that model year. So dunes get eroded. If the overwash occurs, sediment gets deposited in the barrier interior and the shoreline position gets changed. And then we take the new topography of the barrier into the next model year. Okay, so this example on the right here shows 100 years worth of evolution of a natural barrier where we can see the shoreline moving landward over time. It just restarted here. And for part of the time, there isn't the dune line present and there's just overwash all over. And then the dune develops and there's some gaps in the dune and big overwash fans. A key thing to notice here is that even though the shoreline is moving landward, the barrier is not on average getting narrower. And even though sea level is rising, the barrier on average is not getting lower, which is just the result of these overwash processes tending to maintain a minimum island width and height. It constitutes island migrating landward and moving upward with sea level. This model forms part of the modeling framework that we use in this project. And that modeling framework couples this barrier 3D model with a model that incorporates the effects of the sediment balance from a longshore transport and couples with human dynamics modules that represent the management actions that are undertaken in response to storms and sea level rise. So each model year there are some changes to the model topography representing the human management strategies. And this leads into where the beginning of the video describing the project starts. Thank you again.